Hello, everyone. My name is Vincent, and this is my colleague Fokko. For all intents and purposes for this talk, there's a few announcements we have to do beforehand. First of all, we do not work for Blizzard. Second of all, we do not work for Nintendo. And third of all, we do not work for Microsoft. We're going to be talking about an algorithm that's kind of like TrueScale, and TrueScale is an algorithm that has a patent on it, and I'm not intent on figuring out what that means. So these are three public announcements. Fokko is the engineering person, I'm more of the algorithm person, and we kind of had a fun hobby project, and today we want to talk about that. And mainly it's going to involve how you estimate the skill of players in real time and do streaming things. But in a more general setting, the thing we really like to talk about is how machine learning is usually applied in a streaming setting. Very frequently, at least what I usually see from my clients, is that you typically train a machine learning algorithm in batch, and what you would then have is you would have a certain event, and the machine learning algorithm is applied, and you have a tag that's attached to it. And this is great, except for that this machine learning algorithm only refreshes every time we run the batch algorithm. And you might imagine a situation where it would be kind of nice that the machine learning algorithm basically trains for every single event that's being passed in it. So maybe this will be preferable, and what we're trying to explain today is sort of something general about this phenomenon. Because apparently, if you solve it in streaming, you've also solved it in batch. So this could be preferable if you find some sort of general way to kind of solve this. So the enterprise use case we then have in our situation is we are some sort of video game company, let's say, and we have a bunch of people that are sort of waiting in the queue, and they want to go ahead and play video games. This is trickier than it might seem because, sure, you can wait in the queue, and it sucks if you have to wait. What sucks even more is if you then start playing the game, you're playing the game against someone who's like way better than you are or way worse than you are. So in this queue, the queuing thing is important, but the skill estimation of the player is also kind of important. And you don't want to do this in a batch algorithm. You kind of want to have every game update the player skills. And you also need to find a nice way that you can estimate these player skills, but in a streaming setting. So I hope we've got it clear. This is the enterprise solution we'll discuss first. So to make this work, there's a small observation that you would have to figure out. First of all, a skill, let's say we've got very good players, we've got very bad players, and we can basically put a player and map it into like a space between 0 and 1, where 1 would be you're super good, 0 would be you're super poor, and let's say all the players probably fit in between there. The first observation then that's going to help us design the algorithm is to say, instead of saying a skill of a player is a line, just a single point on that axis, it might be more useful instead to suggest that we're going to go for a distribution. There's a couple of things we'll gain, but for now the main thing that's important is that you can realize that you could then also discuss the certainty of a skill estimation. In this example, it's very hard to see how certain you are about the blue line. Whereas here, because it's an actual distribution, it becomes fairly evident that this person probably didn't play that many games, henceforth you don't really know, you don't have that high of a confidence. The green player, though, we're pretty sure that the skill is somewhere in that area. So having a distribution can be helpful, basically as a data structure, but mainly in designing the algorithm as well. So let's say we have a data structure which is just sort of a histogram, and that represents a skill distribution like this. You have one for a certain player, and you have one for another player, and let's suppose that we're dealing with a two-player game in this case. These two one-dimensional distributions of skill can be mapped into a one two-dimensional distribution. And for the probability theory nerds, this is basically just if they're independent of each other, the two-dimensional distribution of these two. And sort of the blunt thing that you could go ahead and do is you can say, if player 1 wins, then probably the likelihood of player 2 winning wasn't that high, and it's probably more likely that this player has a higher skill than that one. So what you can just do is cut away mass there. And that'll be your posterior, let's say. And you can do that as well for if player 2 wins. And kind of a cool feature of thinking about it this way is if there's a draw between these two players, you can actually say, OK, we're going to cut it away from both sides and just take some sort of margin around here. And that's a nice way to sort of communicate to the probability density function that these two players are probably similar in skill level. Again, what we probably do want is some sort of margin, because otherwise we are not going to be able to accommodate for draws. So far, we started out with these two distributions, and then after the game, let's say we have a distribution like this. If we then want to update our player 1 and player 2 skill, the only thing we really have to do is then sort of, np.sum, and then normalize again, normalize all the probability mass back to a one-dimensional distribution. And hopefully, well, we can prove that. What will happen is, if player 1 has 1, the skill will sort of slightly increase, and then player 2 will probably be a little bit less, and vice versa. So, without any maths, I hope I've convinced you, these are kind of nice properties, and these properties all arise from the fact that we're taking a distribution, not a single number. There's stuff that we gain from this. So when you have something like that, you then obviously build a simulation to confirm that your suspicions actually work. So I made this small app. If you download the slides, there's a link. You can play with it online. I basically say, simulate player 1, simulate player 2. This is some sort of skill distribution. That's some sort of skill distribution. And let's pretend that in this case, player 1, 1, and then player 2, 1. You can actually see that the distribution sort of skews one way and then the other way. That's exactly what we want. There's a bit of a bonus, though. And if you're a bit of an information theory nerd, this should become obvious. But the nice thing is, now let's say we have a player that's supposed to be pretty good already. Like, we kind of know that this player won a bunch of games, and this is probably a good player. This can also still be a very bad, or like an average player. But what happens is, if the average player loses from the very good player, the distribution for the good player and the bad player don't really update as much. We haven't learned much from this game. The player who was probably good is still probably good, and the player who's probably average is still probably average. However, what's going to happen here is if the player who's supposed to be average suddenly won from the person who's good, then suddenly the effect of movement is much bigger. We've learned a lot more from this one match outcome. And this is also what you want. If there's more information in a single event, you want to be able to learn more from it. It's not like the gradient step is the same for every single match. And what you can then do, again, more of a simulation, is you can say, let's do the simulation again. This was just for 2 players. Now let's say I have 100 players. Player 0 has skill 0. Player 100 has skill 100. And I'll just let them play against each other randomly and see if I can then have a system that converges. What you see there, I think this is after, I don't know, this was like 100 players or so, and this was after 100 iterations. This was after, I think, 1,000 iterations. These are the histograms. And these are the most likely points for those histograms. And what you see, if we only play a few games, there's still a bit of noise. You want this to be a perfect diagonal line. That way you know that the exact skill has been matched. But you can see that the system at some point converges, which is what you typically want. This is sort of a nice property. Another property, which is kind of nice, sort of you get for free, is that all the skill is mapped sort of homogeneously. It's not like most of the people are sort of in the middle. What this system automatically does for you is it tries to map everyone homogeneously between 0 and 1. Okay, so let's try to apply it on a real data set then, shall we? So what you can do is you can think, hey, Pokemon, that's a fun thing to play around with. And I need training data, so you can go to these fan websites, like pokeapi.com. You can download all this Pokemon data. What you can then do is you can go to a fan website that does nothing more than tell you how much damage one Pokemon does to the other if they just do basic attacks. The formula say that. Also, like, as a constant for if you're water Pokemon, a fire Pokemon, and whatnot. The cool thing about this is then you can sort of do the exact same exercise as I said before, but then you can just simulate it for all the Pokemon that exist and try to figure out which Pokemon is actually the best. This is what the histograms eventually look like, and I can confirm that Magikarp is indeed the worst Pokemon out there, and Mewtwo is up there in the bigger ones, so yeah, I've got the Bayesian proof. This is all great, right? This sort of works. So far, I hope I've not lost anyone, and I hope we're kind of excited. Turns out, though, what I've just done is something that mathematically is kind of general. There is a general maths to all the stuff that I just talked to you about. If we take a step back, I hope we all realize that designing the algorithm became a whole lot easier when we admitted that we wanted to quantify the uncertainty of the skill. That's like the one thing we needed to design all of this. If we didn't use that, this would have been bupkis. This means that we must work with distributions of our state and not just mere statistics. And if you're a Bayesian, which is sort of a school of machine learning, then this makes complete sense. Theta is nothing more than a symbol for all the weights that you're trying to learn. In our situation, theta is the distribution for skill over all the players. And then, being a Bayesian, you always write down this one formula. Given the data, what is my most likely theta? Well, it's proportional to this entire formula. I'm going to zoom in on this formula a bit, because in a small moment I will prove to you that this is always streaming. Basically what we say is we start with some sort of prior. Every player has some sort of distribution that we start out with. And every time 2 players have a game, then we update them. This is sort of the update step for the ith game that we have. So if I then translate that into a situation where I've only seen 3 games, this is basically the same, I just written it out. After careful consideration, you should hopefully notice that the prior for the second data point is basically the likelihood of the first data point times the prior I originally had. This becomes sort of the new prior. For the third data point, this becomes a new prior. And I hope that by now the recursive relationship becomes clear, which basically means that if you have a machine learning algorithm that can be written in this way, you have a recursive relationship, and henceforth your machine learning model is streaming. You get that for free. You still might have some problems with sort of the data structure you have here. We are using histograms, and if you're using probability densities, you might have to consider that, because that's going to be the tricky part. But at least in theory, this is a general sort of cookbook for any streaming algorithms you might want to make. Also, you can tweak a bit if you feel like playing around. You can add like an alpha parameter and a beta parameter. So if you want some sort of a decay in your system where new data points are worth more than old data points, you can sort of fiddle around with that. In general, though, if it fits this, your machine learning model is streaming, and that's kind of nice. So hopefully we all agree that we just saw an example of exactly this. It's sort of a nice general recipe for things to come. So, a small show of hands. Who knows this game? And this is a developer conference, so you guys are totally lying. This is Heroes of the Storm, and this is different than sort of the Pokemon use case we just had. This is a harder problem. That's for 2 reasons. One, there's teams now, and second, you can say, I want to be this character. And certain characters are strong against other characters. So where this was our enterprise use case before, this is now our enterprise use case. So not only is there a queue of people that want to play as quickly as possible, you also have people that say, hey, I want to play as this character, I want to play as that character, and I want to be an assassin, I want to be a healer, and whatnot. So now it gets tricky because we have 2 teams that are fighting, 2 teams of 5 in this video game, which basically means we have 10 skill distributions we have to update. So we're adding noise to the system. We are now also bothered with the problem that we need to have teams. And we still haven't discussed, how do you do the queuing properly. And you might also need to wonder, there's character imbalance. If I have a team with all healers, they're probably going to get pwned if you have a team of all assassins. So there's a couple of angles of problems here. So the way you solve that is you just spend 15 minutes on the whiteboard and come up with the simplest thing you can think of. So let's say there's some queue of people, they keep coming in. I need to grab for every person the skill that they have. Let's say I have some sort of player state. How that's done, Fokko will discuss in a little bit more detail. Given the skill, we can map you into some sort of bucket, and every bucket is kind of a queue. If there are 10 people in this bucket, the game can go ahead and start. Seems simple enough. Then if you have 10 people, assign them to a team. This is a separate problem from that one. They then do battle, and then this has to get updated. Basically, all these steps can be done independently of one another. The way the team is assigned, if you have 10 people, the way that you assign a team, that's independent of how the 10 people got together in the same skill. And that's kind of nice. So if we have something like this, we can also do sort of internal A/B testing. We can have a separate bucketing system. We can have a separate team assignment system. So there's internals you can go ahead and A/B test. And in the general situation, this would sort of work. We just have to describe sort of the small challenges in between. The main ones are, how do you map a skill to a queue? So, player comes in, how do we map the skill to that? How do we assign teams from a queue? And how do we update individual skill after a team fight? Because 1v1 matches, that sort of works, but 5v5 might be different. Going from your skill distribution to a bucket is relatively easy. Just take the peak. That's your bucket. And this is a histogram, so let's say this can have 100 buckets, this can have 8. You're always going to be able to map this. That's a non-issue, that's relatively easy. What's a bit harder is assigning teams. So we have 10 people, and let's say in this situation, every person in the bucket says, hey, I want to play as Uther, I want to play as this character. You kind of want to have a predictive thing that says, okay, probably this assignment causes the most balance, let's say. And this is only based on the character choice that you've made, not you as a skill per se. There's a lot of combinations that are possible, though. And this sort of goes wrong very quickly. So you just come up with a heuristic. Let's say I've got some player in the queue, and this player wants to play as Diablo. In this particular video game, there's types of characters. So you got the healer, you got the tank, you have the assassin, and the specialist. Basically, what you can do is for this player, you can say, this player wants to play that character. That character is a character of that type. It's a map. So let's say these are the 10 characters that we have in the bucket, and we're going to assign these to teams. Basically, you can say what type of hero they are. What you can then do is you can just sort of say, let's sort based on that. Let's sort such the assassins are first, then the tanks, then the healers, then the specialists. And once you have that, 1, 2, 1, 2, 1, 2, 1, 2, and this way you kind of prevent that not one team will not have all healers or all assassins. It's a bit of a dirty trick, but it's actually kind of defendable. And it's simple, which means you can just go ahead and implement it. We can always try out different ways of doing this, but this is simple enough. Updating skill is tricky, though. Before, we had a two-dimensional distribution. And you can imagine that's kind of like a matrix, and you can remove mass, and then you can distribute that back. And let's say we've got 100 buckets for the skill histogram. All that is fine, but if you then do a 10-dimensional histogram of that, that thing's going to blow up in memory. It's going to get quite big. So this would be the probabilistically nice way of doing it, but it's going to be a heavy calculation. Alternatively, what you can do is you can say, take the 5 people from this team, average their skill, and pretend that this player is fighting against the average of the team, and then do the update. Probabilistically, this is a bit shitty, but at least the calculation's light, and we like that. We can also just hire a bunch of data scientists and have them apply all sorts of maths to make an update rule that's sort of solved probabilistically. My experience, though, is you can do all the math and all that's great. Usually this leads to a maintenance risk, though, because not every engineer appreciates probability theory as a PhD does. So I'm not too sure if I like that. So probably this is a good alternative to go for now. And the idea is relatively simple. You just say, look, I've got these characters. We average all of these skills. And when we update, let's say, that player, we pretend that that player was fighting this guy. And being the good data scientist that you are, before you implement any of this, what you typically then do is just run your own simulation. So here's a bunch of distributions that I started out with. The blue dotted line is what you did before. The top players won, these lost. And if you do that trick, it's kind of a nice nudge in a certain direction. And you can tweak some things here and there, but you kind of want a general update rule that works like this. Every time a game is played, this is sort of the effect of an update. So this is what the entire system looks like. We start out with a queue. We map a skill to that. That allows us to put you into a bucket. The number of buckets, let's say, is a hyperparameter. We can tweak that. How we assign a team, we've got a heuristic for that. We can always change it, but we've got that solved. And the main important thing, how to get from a battle outcome to an updated player state, that's something we've also discussed. So basically, this entire circle is done. The thing we kind of need to do now is just engineer it. This guy.
Thank you, Vincent. Personally, I like Python, I like Jupyter, but I love Flink and Scala, so we decided to productionize it a bit and put it into Flink. Everything is written in Scala, the source is available if you like. So what we see here, this is a bit of a logical diagram of the components that you can also translate a bit, of course, to the Flink operators. So what we really liked is that for each step you have a separate operator. So for example, sampling the player skill, you can implement it, test it individually, and then put it in like this Flink pipeline. And it's also really easy to swap out like a certain component with another one if you want to try, for example, a different way of forming the teams. We have a lot of hyperparameters, as you might suspect. So there's a lot of numerics going on. So we have to make sure that we can tune these hyperparameters and also verify them. And what's very important, of course, if you want to implement this at the scale, you cannot do it in Jupyter or Python. Then you need something like Flink. And also the way that we implement it, you can relatively easily scale it up to like a bigger, like more nodes. So if you look at the execution pipeline, the players that are going into the queue are generated by the source function. Then we trigger a rebalance, so our cores of our MacBooks heat up evenly. Then we sample the skill distribution from the Queryable State inside of Flink, so we don't need really external components. Then we have a window function, because certain people are applying, and we have to wait for 10 people that fall into the same skill bucket. Then we simulate the game, and then we split it again, so we can land like the user on a specific node where the value state of the player is. So what we use is the queryable state of Flink. It's really nice, sharded by key. It gives us the benefit that we can also tune the parallelism. Like if we get a lot of more users, then we can reshard the key space and increment the number of executors. It doesn't have any external dependencies. For example, if you want to store this in something like Cassandra, then you have to take care when you snapshot your system that you also store the state of this external component, which is in practice not really nice if you want to if you have to maintain the system. So how did we actually implement this? Quite simple. So first we have this interface of the queue. It's just a JSON message that comes in. We parse it. We sample the player skill. If there's no skill yet, then we take just a normal beta distribution. We shard it by the key. So based on this player, for example, we have 200 buckets of player skill. We search for the max player skill, like Vincent explained, and then we map it to the queue. That's what's happening here. So each of these players lands on the same machine. Well, we wait till we have enough players. Then we do the heuristic that Vincent explained. Then we play the actual game. Of course, if you have a real game, then this would be outside of the Flink system. It would just playing the Heroes of the Storm game. And then we do a flat map, which I will elaborate on later. But this actually from the one team taking the average and also doing the key buy on the player ID. So we can use this average of the opponent team to update the distribution of the player based on if he won or lost, like to the left or the right. And then we have the queryable state that we use to at the sample player skill to read from. So let me give a small demo of how we work. I think I have to go to.
You have to press escape, I think, as well. Oh, never mind.
Yeah, I think this is easier for me. So we have a local Flink running, a job manager and a task manager, because we need a job manager for the queryable state. Let me first go to my project. So right now, we've just simulated a game of 1 versus 1. Let's make it 5 versus 5. So we built a project and submit it to the local Flink machine cluster. So, and we have this notebook, because we found out it's really easy to make mistakes here. And you want to debug your numericals. So if something goes wrong, you have a player that's actually really good, but gets assigned with teams that's really bad. You want to debug how were the distributions, what happened. It looks a bit. I will explain it. On the x-axis, number of iterations. So we have here 100 games. And on the y-axis is a skill. This one is so if you're on the top, this player 5, it's really quite a bad player. On the right, we have player 95, which is a really good player. Of course, Flink doesn't know, of the application in Flink doesn't know if this is a good player or a bad player. It has to derive it by playing the games. What you can see is that it actually quite fastly converges. So after 40 games, then we see like a solid yellow line, which means like a high peak, which means like a high certainty of the distribution. So in the background now, our new simulation is running. And then this is now written to disk. We can refresh the data. And now with 5 versus 5, we see that that we have much more jitter. And it's because, as you can imagine, if you have a team of 5 people, of which 4 are really good and 1 is really bad, then this guy, which is quite bad, it will still win the game because he's with a team of 4 really good people. So this is a bit of the problem that we encountered with playing the team matches. Also, if you it first has to finish, but I will come back to this one later. Let me get to. So this is a bit of the workflow that we used. Like first, Vincent had a basic way of doing it in a Jupyter notebook, but I implemented in Flink, and you still want to debug the system. So what we do now is just dumping all the data of the games to the local disk. If you want to make it a bit more fancy, you of course want to maybe throw this data to Grafana or something like that, and then you can get insights of how the system is performing. Of course, now we're only focusing on how fast does the player converges, but maybe also stuff like how long has this player been in the queue. That's also something that you want to measure, because if people are really stuck really long in the queue, if you have with World of Warcraft, that's really annoying. So you want to be aware of that. And if you don't visualize, you get stuck really quickly for mathematical reasons, but also we have some issues with Flink, which I will elaborate. Before we had like a smoothing parameter, so like Vincent explained, if you take this two-dimensional distribution based on if you won or lost, you cut away the mass of one of the sides, and then we had like a smoothing parameter of like adding a bit of mass to the whole distribution, so you don't approximate, you don't go to zero, because if you go to zero, then you will get 0 point, divide by zero exceptions, and that's something that you don't want. It turned out there was a better way of doing it. This smoothing parameter was quite hard to find the right value. And then this happens. So if you see like this player, now let's take this one is player 10. It's quite a poor player, but you see like huge jumps here, and that's something that you want to avoid, of course, because that tells that the system is really unstable. So what we did instead, we didn't cut away all the mass, but we took like, in this case, if you lose the lower triangle, multiplied it by 3, so you still get like this nice distribution on the upper side instead of just adding this constant. This really had a lot of influence, so you really want to make sure that if you design a system like this, with all the nice Bayesian formulas, that you still are able to see what's happening under the hood. So if we, with the new way of cutting away the mass, you see like that the game converges quite quickly, and even 5 times 5 plays are quite good because they're quite stable now. So that's quite nice. With all these hyperparameters, you have a lot of degrees of freedom. So you want to make sure that you test them, preferably like offline, not in a whole Flink system that you have to start up and clear every time. Because especially with the Queryable State, you cannot start it locally inside of your process. You have to have this cluster running on your machine, which you have to package the SVT file and send it to the cluster, which is takes quite some time. Instead, if you do it on your Jupyter notebook, then you can have a really fast round trip. Also, we had a different problem. So I had the simulator, which I didn't have any delays in there. So when I started the game, the simulator would produce a lot of games, and this would mean like that for one player, he would be playing like he could be, for example, like 10, 20, 50 times in a queue, which is, of course, in practice, not possible at all. Maybe if you're a really good player, then you can play with 2 laptops simultaneously, but I'm not capable of it. So what happened is that this map skill is a quite easy operator. This mapping to the buckets is it's quite easy. This team assignment is just a sort of 10. But then after the battle, what happened? Then you have to make this 2-dimensional distribution, which is a bit heavy. So there was like a big back pressure here. And what happened, like this same player, he was sampling old state because the updating of the state was really slow because it took a lot of time computationally. But this player, because there was no the simulation that submitted the player to the queue, didn't have any how do you call it?
proper knowledge.
We introduced the delay there, so you wait till the player has finished his game, and then it worked. And then you think you're debugging all the numerics, but then it turned out it was Flink that was causing this error. So this is something that we learned, and yeah, it's not always in the numerics, but also with this back pressure thing, that your queue is just really full. You have to be aware of it. Yeah, like I already said a couple of times, you need to visualize. You have to be extremely scientific. For example, we had a couple of bugs where we forgot to normalize like a distribution, and then it explodes. So you have to be really sure about this, and this is also really nice with Flink that you can really just unit test all your software. Yeah, and we started first with the 5 versus 5 games because Vincent on his notebook he implemented the 1 versus 1, so like do the 5 versus 5 game right away. But it's also smart to start simple and then go to the team games. So this is one of our end result. So this is the actual skill level. So this is what's hidden in the data set, but Flink doesn't know. And this is the estimated skill level after 100 games. You see with that for the first 1 versus 1 games, it converges quite good. Ideally, it should be like a straight diagonal, but we think that there's still a bit of a swinging there because we start from a better distribution. And if you go into a 10 versus 10 game, so that's quite a hard problem, then you see that there's still a lot of jitter. But you can imagine if you have like a game with 9 very good people and 1 really bad one, then it's really hard to find out that this guy is really not as good as he claims to be. So the problem what we're trying to solve, if you go a bit in helicopter view, so we want to have a reasonable waiting time, so people are not too long in the queue. But you also want to make sure that people, most of the time, they have a 50-50 chance of winning or losing a game. So you don't want to have a very short waiting time with a high distribution of people who only win or only lose, because if you only win or only lose, you will be bored quite quickly. But you also don't want to wait too long. So in this case, the upper right would be the ideal situation. And for us, this was a nice, fun exercise to learn about Bayesian models and also learn about Flink and the Queryable State. What we're trying to convey is that if you have a model that you can express in a Bayesian formula, then you can also really implement it nicely on Flink. And also in other streaming engines, of course. It was not too hard to port it to Flink, actually. I think it's a very nice API. Maybe the Scala support could be a bit better, but it's also something that we also work on. What's really important is that when we start a game, we start with 1,000 new players, and it's just like a green field. So if you have a system where you already have like a couple of players and you add more players, it's more likely that they will converge quite quickly because the system is already stable. And if you add more players than new players, then it will be okay. Like I said a couple of times, if you also design such a system, you might sometimes want to do some fancy mathematical stuff, but also with the team assignment, you can think of something more simpler, like just sorting it and make an even distribution. That was our talk. I hope you enjoyed it. If there are any questions, feel free. Also, the code is on GitHub of GoDataDriven, so thanks.
Any question?
So you talked about that when you try to run it distributedly in Flink, you can encounter several other problems, but you would also like to visualize and debug your code.
Yeah.
And was using Jupyter fast enough for development loop, like just logging from Flink or in Scala and using that data in Jupyter? Or have you tried other ways to do it, like for example in Zeppelin, using Zeppelin and Flink directly in such cases, or you've tried it and you did not like it?
I ran Flink in Zeppelin, and it worked. But yeah, the thing is here, we have to go to you have to start a Flink cluster. So you have to go to the bin directory and do the start cluster. Otherwise, you don't get like this job manager, and you won't able to use a distributed state. And to debug this system, you really have to run the application. You cannot. Of course, there are ways around it. You have to mock this queryable state, but that's, I think, a lot of work to do that.
And to add to that, some of the plots we make are kind of creative and not standard line charts. And we want those non-standard plots because they help us debug. And Zeppelin doesn't have the greatest support, let's say, for tile plots, which we definitely needed. So from the get-go, we just figured logging to disk is fine.
Okay, thanks.
Keep it simple.
Thank you for your talk. It was really fun and interesting. I have one question, like leading in the direction of Gabo's talk, going in the direction of loops. Basically what you have is a loop, right, in your program there. Did you also try the iterations of Flink, or what was the reason you didn't use these?
I haven't worked with the iterations of Flink. For us, first when we designed this, we thought, we need some external data stores, for example, stored in Redis or something. But when at that time Queryable State was just released, so we decided to work for that. It's not a. Maybe you can also do it with loops. I saw 2 presentations ago that you can run into deadlocks, but it's a good suggestion, I would say.
Well, one small thing, I guess, to add to this, all of this is sort of asynchronous. It doesn't matter in what order things happen, let's say. So if one message gets in late, it's still fine. You get its equivalent. So if A happens before B, the posterior is the same as B happens before A. So that also makes it easy to just do this.
Cool, awesome talk. So guys, recursive iterations, you're updating your posterior distribution all the time, yeah? What kind of likelihood do you use for that? Because in
it's
streaming...
a histogram.
Sorry?
It's a histogram.
It's a histogram.
That's
Don't do any exponential families or like sufficient statistics, because here you have to have a proper number of that to get convergence.
So to anyone who doesn't appreciate the math, forget what I'm about to say.
Gotcha.
The best way to do this is to have like a multidimensional beta distribution, but finding a proper closed form solution for that is hard, and I checked all the pages in the Matrix cookbook. So we just went with this, because also for debugging reasons. Sure, you can do like a beta step update, and if you have it in high dimensional space, all that stuff might work, but now we can actually visualize the freaking histogram, which is nice, because then it makes the debugging a whole lot easier.
Yeah, neat. But I saw also something more informative, was the shape and the density of your distribution when you show me the graph with the correlation, in fact.
So we initialize with a beta 1.5, 1.5, because then it's not flat. And it's
flat.
Yeah, so that's what we use. But from that point on, it still stays kind of like a beta shape, but we don't know what the parameters are. We just keep it in histogram. Which is something we could improve upon, but for demo purposes and keeping things simple, it's fine to start with.
Yeah, but this is why choosing a different likelihood maybe helps you to reduce the number of parameters you have in the number of parameters.
True, but then it helps if you have a closed form solution on how to get the posterior.
Yeah.
That's the naughty thing.
Cool, thanks.
Well, one thing I would add about this, though, like right now we're doing this with histograms. Of course, if you want to do linear regression this way, there is a recursive function for that, and then you just work with normal distributions, because the histogram will obviously fail. But this is a very nice example where the scales are always between 0 and 1, and henceforth the histogram also just makes sense because of that. Doing this recursive stuff is more of a data structure problem than a probability thing problem. Yeah.
So the queryable state feature is traditionally for querying the state from external services. So an application queries the state of the Flink job. But do I understand correctly that you queried the state from another Flink operator, right?
Yes. Yeah.
And did you encounter any additional difficulties because of this? So for example, did you need to use the async IO feature of Flink also maybe? Or did it work without that?
Yeah, as far as I know, it's just in the process call. So it's just, I'm not a queryable state expert, but when you issue a query, you don't know, because this key space is sharded, we shard it by the player ID. So based on the player ID, it's one of the JVM processes. When you query the state, you connect the job manager, and then you ask like, where's this key, on which machine does it, on which process does it reside? And then you can query it from there, like a read-only yeah, query. Does that answer your question?
Yeah, thanks.
Your problem is not too different from rating chess players, for example.
Oh, yeah, so this is the TrueScale was like to replace ELO, kind of. It's true. This is the one thing that makes this a little bit different is we accommodate for teams and we also allow for draws, which I think, if I'm correct, ELO doesn't. That's like the one difference, but it's very similar. Yes, that's true.
Thanks.
Hi, great presentation. Thinking about the improving of convergence of team versus team, have you thought about sort of looking inside the games and maybe what implementation ideas you'd have to see who made what decisions?
So currently we just simulate this ourselves, right? So we also have a log of Heroes of the Storm data that we could do stuff with, but I don't have the database of all the Heroes of the Storm games, and you definitely, but right now what we're sort of trying to do is make sure the game is balanced, but what you can also do is during the game try to predict the game outcome, who will win, but we don't have inter-game data. I do know that there's betting competitions for this. So if you have like the #1 US team fighting the #1 Korea team, which is like the match, I've been told, then you do have these betting companies where they sort of mid-game say, okay, I'm betting this much that this team will win by that time. There's all sorts of crazy things happening there. So there are people who are doing similar stuff like that. We don't have that data.
All right, thank you.
It's still on the list to do.
Yeah, there's like so much you could do with this.
Okay, I have one suggestion. Like, as you say, you don't have the real data. So, for me, like, I'm from South Korea, and there people are using like crazy about online gaming, and there are some companies only they provide some APIs for their data, but I think you will have some difficulties because some of the material is in Korean. So like maybe you can get some of that.
So actually I have like a gig of logs actually. There's this website called HOTS Logs, Heroes of the Storm Logs. And the idea is you just send your video files from your own replays to them, and then they will sort of analyze it, figure out who won, and then if you go on Reddit, you find a guy and he'll post this. What they also do is they have sort of more of an actual MMR score that they have for the player, so we could use that to cross-reference that with our system. But you know, this talk was already like 80 slides. Yeah. So some other moment in time.
Okay, one thing is like after this we will have a lunch break, and let's thank the speaker.